Good afternoon, students. I am Dr. Ekta Jain from the Department of Physics, Barkatullah University, Bhopal. Today, I am here with Statistical Mechanics, which is one of the most important paper from the syllabus of MSc Physics. Now, I will teach you unit number 4, phase transition. And in this unit, I am going to cover the following topics like phase transition, first order phase transition, second order phase transition, critical exponent, scaling hypothesis and Ising model. So, the journey starts from phase transition. A phase transition is the transformation of a thermodynamic system from one phase or state of matter to another one by transfer of heat. During a phase transition of a given medium, certain properties of the medium change, often discontinuously, as a result of the change of some external condition such as a temperature, pressure or others. For example, a liquid may become gas upon heating to the boiling point, resulting in an abrupt change in volume. And now I am going to tell you about that factor which is very importantly required for the phase transition. So, for the phase transition to occur, energy is required to partially overcome the attractive forces between the molecules in a solid to form a liquid. That same energy will be removed for freezing to take place. So, in general, simple substances are capable of existing in phase of three types: solid, liquid and gas. Here in the figure, we can see that the three lines in a phase diagram separating these phases are called equilibrium lines. And here we also can see a common point A where lines meet, called triple point. At this unique temperature and pressure, all three phases coexist in equilibrium with each other. Point C is the critical point at which liquid-gas equilibrium line ends. Here we can see that this point C where liquid and gas, where this line ends. So, the volume change del V between liquid and gas has then approaches to beyond the C, and there is no further phase transition since there exists only fluid phase. For the as far as my knowledge is concerned, there are 6 changes of phase that substance go through. First, freezing. It is for the liquid to solid. Melting. It is for solid to liquid. Then condensation. Gas to liquid. And then vaporization. Liquid to gas. Then sublimation. Solid to gas. And then deposition. Gas to solid. Now, I think the sublimation might be a new word for some of you. So, what is sublimation? Sublimation is a chemical process where a solid turns into a gas without going through a liquid stage. An example of sublimation is when ice cubes shrink in the freezer. And this is very beautiful example because we can see this in our daily life, that when we froze the ice, the water directly goes to the ice without changing in the liquid. So now we come on the first and second order phase transition. So what is first order transition? In first order phase transition, there is discontinuity in first derivative of Gibbs free energy, while in second order transition is continuous with first derivative, but there is discontinuity in the second derivative of Gibbs free energy. And the fine difference between the first and second order phase transition is that in first order phase transition, entropy, volume and energy of the thermodynamic system change abruptly, whereas in second order phase transition it changes continuously. As in this table we can say that in first order phase transition there is discontinuity in the first derivative of Gibbs free energy. Here for the first order phase transition it is written S over here. So don't get confused, as I am telling that in first order there is discontinuity in first derivative of Gibbs free energy. So S is the first derivative of Gibbs free energy and S is equal to dG upon dt. Now, the various solid, liquid, gas transitions are classified as first order transition because they involve a discontinuous change in density, which is first derivative of free energy with respect to the pressure. For the example of second order phase transition are ferromagnetic transition, also superconducting transition. For a type 1 superconductor, the phase transition is second order at 0 external field, and for type 2 superconductors, the phase transition is second order for both normal state and mixed state. Here in the figure we can see that there is some discontinuity in first order phase transition while the first order derivatives are continuous in second order phase transition. When we study the phase transition, the critical exponents play a very important role. So, what are critical exponents? Actually, critical exponents describe the behavior of physical quantities near continuous phase transition. They are universal, that is, they do not depend on the details of the physical systems but only on some of its general features. I have highlighted the four most important critical exponents. The first one is critical exponent alpha. It is used for what? It is associated with the behavior of a specific heat in the vicinity of the critical temperature. And now critical exponent beta. As T approaches to Tc, the density difference across the coexistence curve varies, is associated with beta. Critical exponent gamma, it is related to the critical behavior of generalized susceptibility. While the critical exponent delta, we will study it in two parts. Part A, it is associated with the relation between external magnetic field and magnetization at critical temperature, and the relation is shown by this equation. Now part B, it is also associated with the pressure and density at critical temperature. The relation is also shown here. This is the relation for critical exponent delta. Now, where is the relations for alpha, beta and gamma? So, my next slide presenting a table for the critical exponents alpha, beta, gamma and delta along with their Ising values. After critical exponents, one most important parameter is scaling relation. So, why we use scaling relations? To reduce the independent number of different exponents, scaling relations are used. And here in this table, I have given two scaling relations which is shown here on the slide, which is given by the different physicists like Wisdom's law and other one. Now, we have studied phase transition, first order phase transition, second order phase transition, critical exponent, scaling hypothesis. Now, the last but not least, the topic comes Ising model. So, in this slide, I want to highlight I want to give some highlights about Ising model. So, the Ising model, named after physicist Ernest Ising, is a mathematical model of ferromagnetism in statistical mechanics. This model consists of a discrete variables that represent magnetic dipole moments of atomic spins that can be one of two states, either +1 or -1. And as we know, +1 for spin ups and -1 for spin down. The spins are arranged in a graph, usually a lattice, where the local structure repeats periodically in all the directions. It allows each spin to interact with its neighbors. It means the particular spin will influence by its neighboring spins only. Neighboring spins that agree have a lower energy, but heat disturbs this tendency. It means when we apply heat, this tendency will be disturbed, thus creating the possibility of different structural phases. This model allows the identification of phase transition as a simplified model of reality. So, there are some more important points about Ising model. For study the Ising model in detail, we consider a ferromagnetic substance like iron and nickel without any external magnetic field being applied. Sum of spins of the atoms becomes spontaneously polarized in the same direction below the Curie temperature. This creates a microscopic magnetic field. The spontaneous magnetization so created vanishes if the temperature is higher than Tc, because the thermal energy makes some aligned spins to flip over. It means below the critical temperature, there were alignment of the atoms, and when we increase the temperature, the alignment get disturbed. Thus, spin get orientated to at random and no net magnetic field is produced. As Curie temperature is approached from both sides, the specific heat of the metal approaches infinity, and the transition from non-ferromagnetic state to the ferromagnetic state, called the phase transition of second kind, and is associated with some kind of change in symmetry of the lattice. For example, in ferromagnetism, the symmetry spins is involved. Here I am showing you a figure in which we can see that the three models has been given by the three different physicists, one-dimensional, two-dimensional and three-dimensional. Here we can see that at low temperature there is the aligned spins, while when we increase the temperature, the alignment get disturbs. So the first dimensional model has been given by Ising in 1925, while second dimensional is given by Onsger 1944, and third is given in 2000. So, for the mathematical study of Ising model, we are considering an array of n fixed points called lattice sites with a spin Si, where I is equal to 1, 2 to n, which is only a number either +1 for a spin up and -1 for a spin down. And the Ising model defined an energy for the system as written in this equation, where subscript I stands for Ising and symbol Ij denotes the nearest neighbor pairs of spin, where epsilon Ij is the interaction energy and mu h is the interaction energy associated with an external magnetic field, and for spontaneous magnetization h is equal to 0. Here I have given some specific conditions like if Sij greater 0 means the interaction is ferromagnetic. If it is less than 0, the interaction is anti-ferromagnetic. If it is equal to 0, the spins are non-interacting. Similarly, I have given